Okay, the second type of multiplication operator when you're dealing with vectors is called the cross product. The way it's being defined is u cross v is equal to magnitude of u times magnitude of v times the sine of the angle. So very similar, except that this is actually a vector. So we start with two vectors, we take the cross product of those two vectors. This time we don't end up with a scalar, although this part is a scalar. We need to multiply it with a unit vector. And the relationship between that unit vector E, or any vector, and u and v is that u is perpendicular to v. Wait, no. E must be perpendicular to u, and E must be perpendicular to v. But u and v do not have to be perpendicular. So, cross product is a vector, while the dot product was a scalar. Remember the two cases that we've discovered with the dot product? We have similar cases if you have those two vectors u and v which are parallel to each other, then obviously the angle between those two vectors theta is 0, and the sine of theta becomes sine of 0. Therefore, when u is parallel to v, u cross v is 0. And when u is perpendicular to v, that's when we get the maximum value for the cross product. It's just going to be equal to magnitude of u times magnitude of v times sine of pi over 2, which is 1, times the unit vector. So if you have vector u and a vector v, the cross product, and this is the angle between those two, the cross product is a vector which is perpendicular to u and perpendicular to v. Now, in which direction is that going to be? It could be up, or it could be down. Now, to figure out which one it is, we have to stick with the convention. So if you are in the US, the convention is the right hand rule, or the screw rule. If you're in Britain, then it's, I guess, the left hand rule. Or it's the opposite. Imagine a screw. Imagine that you put your coordinate system on the head, I, j. If you unscrew the screw, so you're going counterclockwise, the screw is coming up. Therefore, the k vector is in this direction. If you are going the other way, so you're screwing the screw in, so you're going j towards I, you end up with minus k. So by convention, in the US, when you have I here and j here, you calculate the cross product between I and j, you end up with a vector k, which is in this direction, out. And when you calculate j cross I, you end up with a vector in the opposite direction, which is minus k. To remember which one is which, you can draw that little screw. You can use the right hand rule, or you can use this ijk, ijk, ijk. As you go towards the right, it's positive. So I cross j is equal to k. J cross k is equal to I. K cross I is equal to j. And if you go the other way, k cross j, we should get minus I. J cross I minus k. I cross k minus j, etc., etc., etc. We have similar rules as with the dot product. We have the associativity rule, which state that if you have a scalar multiplying the cross product of two vectors, then you can distribute the scalar to any one of them. So you can multiply the scalar by the first vector and then take the cross product, or leave the first vector alone and multiply by the scalar times the second vector. You also have the distributivity rule, which state that if you have vector u cross the sum of two vectors v and w, then u cross v plus u cross w. So you take the first vector, you cross it with the first vector within the parentheses v, and you add first vector u cross the second vector w. Okay. So now if we deal with ijk, remember by convention we always choose orthonormal current system, which means that I in magnitude is equal to j in magnitude is equal to k in magnitude, and I is perpendicular to j, which is perpendicular to k. So I cross j will give you k, j cross k will give you I, and k cross I will give you j. If you happen to have the same unit vector, I cross I, you end up with 0, and this is the 0 vector. If you have j cross j, same thing as k cross k. Okay, so this definition again refers to the case where you're being given two vectors in magnitude and the angle. Now, if you're being given two vectors in component notation, now that's a mess. So let's see how that goes. We're going to see the brute force method and the matrix method. So let's imagine A is AXI plus AYJ plus AZK. B is BXI plus BYJ plus BZK. Same thing. Every term will cross every other terms. So we're gonna pick up 9. So let's do it on the fly. First term, AXI cross BXI. I cross I, that should give us 0. So the first term goes to 0. Second term, AXI cross BYJ. We have I cross J, so let's keep that. AX BY, and then I cross J. Then we have the third term, AX BZ times I cross K. Then we're going to have AYBX J cross I. Now the difference between the cross product and the dot product is that dot product commute. It doesn't matter whether you write I.J or J.I. For the cross product, it matters. Because remember, if you interchange two vectors, then you pick up minus sign. So I cross J will give you K, but J cross I will give you minus K. So we need to watch out the order. Make sure we keep track. So the second term is AY/BY J cross J. This guy is going to give us 0. And the last one is AY/BZ J cross K. And the last 3, AZBX K cross I plus AZBY K cross J, and then the last term is AZBZ K cross K, that gives us 0. So we need to evaluate all those cross products. So IJK, IJK, IJK. First one, I cross J. I cross J will give us plus K. So AX BY times K. Second term, I cross k. So I cross k, we're going towards the left. I cross k will give us minus j. So minus ax bz j, j. J cross I, we're going again towards the left. That should give us minus k. So minus aybx k. J cross k. Now we're going back towards the right. J cross k should give us plus I. So plus aybz I. K cross I. K cross I going towards the right should give us plus j. So plus azbx j. And k cross j. K cross j, we're going towards the left. It should give us minus I. So minus azby I. Okay, let's group all the terms together. So let's group all the i's, all the j's, all the k's. We have two of each. So a cross b is equal to, let's group this one and that one, aybz minus azby in the I direction. We have two terms in j, plus azbx minus axbz in the j direction, and the last two, this one and that one, axby minus aybx. Yeah, so that's a mess. You don't want to memorize that. So, a better way. Matrix. Let's imagine you have those two vectors, a cross b. We're going to put our unit vectors on the first row, I, j, k. We're going to put the first vector on the second row, ax, ay, az. And second vector on the last row, bx, by, bz. And here you have two options. So let's do one method first. The idea is to remember that the first one is positive, first term positive, next one has to be negative, whether you go towards the right or down. And then the next adjacent must change sign, positive. So the next one here must be positive, next one down should be negative, this one should be positive, this one should be negative, and this one has to be positive. So that's the convention to figure out the sign. The idea is to imagine for the first term that you have a vertical line going through the first column and through the second column. And what you want to do is use the fish. Up. So the first term, I, which is plus, will give you ay times bz minus az times by. Ay bz minus az by. Second term, do the same thing, except now you imagine a vertical line going through j and horizontal. So now you have a 2 by 2 matrix. We know how to deal with 2 by 2 matrix. But now this j is negative, so minus j and an ax bz minus azbx. And then last term, vertical line going through the k, horizontal line, you're left with a 2 by 2 matrix. Use the fish again, ax times by minus ay times bx. And this k is positive. And this should give you that one, same thing. Except this method is a little bit easier. In case you forgot, if you have two vectors A, B, C, D, the determinant of this is our fish method, AD minus BC. So that's what I used earlier. Now, look, this is a 3x2 matrix. We put ijk here, all the A component, all the B component, and the result is a scalar multiplied by a vector, another scalar multiplied by another vector, a third scalar multiplied by a third vector. So now let's imagine that you have this. Then really all you have to do is put ax, ay, az, bx, by, bz, cx, cy, cz. And instead of having your ijk, you're going to have your ax here, your ay here, minus ay, and your az here. So you can calculate the cross product or the dot product of the cross product using a matrix. Keep that in mind when you're going to be doing cross products. If you're dealing with 2D, it's trivial. Let's say if you have vector R, force F, and you want to calculate the torque between those two, which is expressed as the cross product between R and F. The convention is that F tends to make the R vector rotate counterclockwise, which is our positive convention. Therefore, the cross product is positive. If F tends to make R rotate in the clockwise direction, then R cross F will be negative by convention. So when it's 2D, it's no problem. When it's 3D, it's a mess to try to figure out where the plus sign goes, where the minus sign goes. So I would suggest, whenever you're going to be dealing with torques or couple, take the habit of writing your torque always in a matrix functional form. Then you don't even have to think about it. All you have to do is make sure that you put the right components in every elements. There is a nice property between the dot product of the cross product, which is that if A dot B cross C, you can interchange all the terms. So you can move the A, put it here, kick the B out. As you kick the B out, you put it in the C, kick him out, and then the C has to go somewhere. It's gonna go back here. So really, A dot B cross C is the same as A cross B dot C. And then you can do it one more time. Move all those guys around. So the B is gonna go in the first place, A is gonna go in the last place, C is gonna go in the second place. All those guys are the same. If you start interchanging the position of 2 without changing the last one, you pick up a minus sign. Or if you have A dot B cross C, it's going to be equal to minus A dot C cross B. So keep in mind those properties, they might come back later on.